to open this session on technosignatures. Unfortunately, our first speaker is ill and will not be able to give this first talk on artificial illumination. So we propose that for the first 15 minutes, we open a discussion on the search for biosignatures and technosignatures and what are their likelihood of success and why. So the people on Zoom are welcome to contribute, of course. Yes, Adam. Hello. Hello, George. So what do you think? Do you think it's more likely that we would first find a biosignature or a technosignature, and why? Does anybody want to say something? Yes, Adam.
Well, I just want to bring up the paper that our group, the CATS group, just put out. Jason was the first author, where we looked at the difference between those and looked particularly at the priors that go into it because of the way that the Drake equation is set up, which is sort of linear from stellar evolution all the way through societal evolution. There's this sense that technosignatures will have to come later after the evolution of life, which of course on one level is true. But what we tried to show there is that there's a fundamental distinction between technosignatures and biosignatures, which is that biosignatures always go with their biospheres. If the biosphere dies, the biosignature goes away. And you're not going to find biosignatures someplace else other than where the biosphere is. But technospheres, if we think of them as the planet where the civilization that created the technology was, and technosignatures are totally different because Earth already has technosignatures distributed across the solar system. We have 5 of them that have left the solar system. So what that shows is even with a single civilization, a single technosphere could produce, untold numbers of technosignatures that could be distributed throughout the galaxy that will be still potentially detectable even after the civilization dies. So this is not to say that technosignatures, you should search for them instead of biosignatures. It's just that it's quite possible, that technosignatures will be easier to find and will be more numerous than biosignatures. So we're just throwing that out there.
Wonderful. Yes, there is a microphone at the back of the room, so you can just raise your hand and you'll be given a microphone.
So I guess while you're all thinking of questions, even though I'm a co-author on the paper Adam just mentioned, I'll just, for sake of discussion, the other problem with technosignatures that's brought up is how could these be long-lived, or what are long-lived technosignatures? And so even the idea that a civilization could leave its home planet, you could imagine that that's possible, but then it's not sustainable. So in order to find technology, it has to be something, for astronomy, it's hard to find things that are transient when you're doing long integration times. So you're going to find something that's kind of in a steady state. And so things like combustion might not be the best technosignatures. We have a paper where we talked about farming as maybe a longer-lived technosignature. We talked about chlorofluorocarbons, which might not be long-lived, but maybe they are long-lived if you're using it to terraform a planet. So these are some of the questions that I think are research questions, like what are long-lived technosignatures? Because I think Adam's right, they can leave their planet, technosignatures, and they could potentially be less ambiguous than biosignatures. But if they're not long-lived, then it might be hard to find. So that's one of the questions that hopefully you'll come up with some new ideas.
Jacob, I was actually wondering, how long is the farming biosignature that you guys, what's the time scale for that?
That's one of the ones that we like for being long-lived. You could farm a planet as long as there's a hydrological cycle and a carbon cycle. The technology of farming is adding nitrogen to the soil, and the technology we do that through today is the Haber-Bosch process. So you take nitrogen out of the air to make ammonia through an industrial reaction. And you can power that with solar power. You can get natural gas or other electrolysis from water to get the hydrogen. It's essentially an unlimited reservoir of nitrogen. So yeah, you could really technically have technologically supported farming as long as your population stays sustainable. You can't have population growth indefinitely, but you could have farming as long as the planet is habitable. So you could probably say something about the Delphi.
Hey, Jacob. I just wanted to ask you and the audience here that we thought about some technosignatures that we could potentially detect with upcoming or planned telescopes. I just wanted to ask the audience or anyone if they have any ideas about what kinds of technosignatures that you can think about that humanity right now is producing that we would be able to detect if we place Earth at 20 light years away or something. Do you happen to know? Oh, there you go.
So I remember at the last episode, I'm Tessa Fisher, I'm a PhD candidate at ASU. I remember at the last AbSciCon, when Giada Arni was giving a plenary, that depending on the design they go for, Plato may be able to pick up city lights, like on Alpha Centauri, and I don't remember if it was within a 5 light year radius. So that was the first one that comes to my mind anyways.
That was exactly the talk that was supposed to be in the first talk. And Thomas, unfortunately ill, otherwise we would have.
Steve Croft, UC Berkeley. I mean, sorry to be old-fashioned here, but radio signals and lasers, of course, as well. I mean, that's sort of been, the classical search methodology for radio SETI going back, looking for narrowband signals. There's been some work that's been done that I'll mention briefly in my talk this afternoon by my colleague Michel Gajar at Berkeley and collaborators about broadband pulsed signals mimicking FRBs, but with, there's a sort of classical dispersion sweep for FRBs, but you can sort of mess around with the direction of that sweep and have things that would show up in searches for FRBs that obviously look artificial. So, radio is still a good way to go. It's still a very sort of energy efficient way to go. And I think, we also have a couple of students here who've been working on laser line searches with the automated planet finder that was posted downstairs today. So let's, while we're thinking up all of this other cool stuff that we could be looking for, let's not, forget that even though radio searches and optical searches haven't succeeded thus far, it doesn't mean that they're not going to, especially given how expanding the parameter space that we're looking for.
I have a question about radio, just while we're thinking about it. Do you think that there could be any false positives for a narrowband radio signal?
I think, the main issue, as we saw with the BLC-1 signal, the signal that was picked up at the Parkes telescope in breakthrough observations last year, is that we're sort of deafened by our own technology. So I think that's still going to be the main problem, that we could be sort of confused by something of terrestrial origin that just happens to mimic the kind of signals that we're looking for. And I mean, one sort of analogy that I've come up with, you're walking along a gravel path, and you get back to your house and there's a stone in your shoe that's like the exact right size for the little kind of gap in the tread of your sole. Well, that stone wasn't just waiting for you to come along, it just happened that you walked over 1 million of them and that was the one that fit, right? So you have a matched filter, you're looking for, a narrowband signal, for example, that only appears in observations of a particular star, and every once in a while, just from sort of the trials factor, basically, you're going to get something that looks pretty convincing. I think it's sort of encouraging that the techniques that we have to sort of do interference rejection are, maybe they're even sort of a little bit too overzealous, and we've sort of thrown everything out. And things like BLC-1 sort of made it through, very careful examination by Sophia Sheikh, who led a paper on that in Nature. Ultimately, it's consistent with being human-generated interference. But I think, if we got to the next stage where we say, okay, this is still interesting, we're going to put it out for follow-up, somebody else, some other team with a completely different instrument is going to go and look at the same target. If you observe, Proxima Cent with a completely different telescope on a different day and saw a line at the same frequency and the same drift rate, then I think that's when people start getting excited. We've not sort of reached that stage yet, so maybe it's sort of not a big problem.
And so if you found that, would there be any other like non-RFI false positives that you could think of? Like, why are we seeing this narrow band radio signal for Proxima Cent B and we ruled out all RFI? Like,
I mean, I think
it seems convincing to me. I'm just kind of wondering.
I mean, there could be some other new physics out there. I mean, I guess when pulsars were first discovered, maybe jokingly they labeled them little green men, but, what could be sending out this regular pulse? We don't know. We don't know it's a rotating neutron star. The narrowest lines, if you're doing a narrow line search, the narrowest lines are astrophysical masers that are, at their narrowest, only a few hundred hertz wide. But if you're looking at something that's a few hertz wide that has some sort of nice, clean Doppler signal associated with it, then I think it's hard to come up with an actual process that makes it possible.
Thanks.
I want to ask if anyone else have any comments on it, on Steve or Jacob's. Oh, Adam. Okay.
Actually, I would just like to ask, for discussion about the difference between, classic SETI, I mean, going back to the beginning, was looking for, in some sense, beacons. Like there was the idea, so much, at least in the popular mind, people think of SETI as being about like communication. And in fact, that was, of course, the title of the meeting that the government asked Drake to organize, interstellar communications. But it seems like we're really, especially with exoplanets now, that's not really what we're thinking about anymore. And I just wanted to get some sense from people about the distinction between looking for, it just feels like even the idea of technosignatures takes us beyond really thinking about communication. The communication is not really the emphasis on what we're doing now. And I just don't know if anybody has any comments about that, or how should we be thinking about it? Is that a message we should be, sort of making clear? Because biosignatures clearly aren't. We don't expect biosignatures to be sending us love letters,
Anyone want to comment on that? Yep, that's it.
Yeah, I mean, I think we're pretty agnostic, with breakthrough listen as to whether it's sort of intentional, whether it's a beacon or not. And to sort of push the analogy maybe in a different direction about sort of stones in your shoe. I mean, sometimes people say, SETI's a fishing expedition, and I say, yeah, great, let's go fishing. I mean, let's go fishing with a net and with a rod and line and different kinds of bait and, different sort of sizes of net and mesh and whatever, and see what we can troll up. And it's definitely important as well to sort of motivate this with hypothesis testing. I mean, I think, imagining what kind of signals might be out there, imagining whether there might be, deliberate beacons or whether we're sort of eavesdropping on communication. This idea of, planetary transits or alignments where one planet could be talking to another, and we might end up just sort of picking up signals that weren't intended for us. And sort of getting yourself in ET's head, I think, is a little hard. And, it's something that we spend a lot of time doing. And obviously, sort of, as I'm saying, the ideas that you and others have come up with for the sort of non-communication SETI, including modification of planetary atmospheres and that kind of thing is very interesting and very motivating for sort of piggybacking those kind of searches on biosignature searches as well, and the kind of atmospheric studies that are going to be done by the next generation of telescopes. But, I'm also happy personally, and again, sort of betraying my bias here, just to kind of cast a wide net and see what comes up, right? And maybe they're beacons intended for us, or maybe they're, the galactic internet or something that we just happen to kind of end up in a beam.
Yeah, that's an interesting point, because it's the idea that it may be communications that we detect. It's just not for us, right?
Yes. So it's 15 past, maybe. So we will go to the first talk this morning. And it's the talk by Ravi Koparapu on nitrogen dioxide pollution as a signature of extraterrestrial technology.
You go.
Yes.
All right, thank you, Jacob and Clemo. And thank you for coming here. I'm going to briefly discuss about a paper that we published last year on how atmospheric pollution can be used to detect extraterrestrial technology. I'm going to go ahead and advance a slide here. These are my collaborators and co-authors on this paper. Some of you are here, and thank you for providing your input here and making this paper a really fun project. This is a class of technosignatures that I think we've had mentioned some time ago in the literature, but not in a way that we discussed it the reason for that was that the paper in this paper we were thinking to discuss about how we can use the atmospheric pollution as a detectable means of technology rather than just discussing that, oh, okay, there's pollution, so aliens can potentially emit these atmospheric technosignatures. So gases from this industrial activity observed in the atmospheres of exoplanets are one of the things that atmospheric technosignatures, and this is a passive search we just discussed with Steve and Jacob. They don't have to do anything. They just can go on about their lives, and we just need to point our telescopes to that planet and then see if there is any atmospheric technosignature in there. My thinking is that a planet with a radio technology may also be an industrialized one. And so if you detect one, you might want to look for the other as well, just like, based on our Earth's example. And why is Earth's example good? Because that is the example we take even for biosignature searches too. We are looking for biosignature, Earth-like biosignatures as a standard template because that's the only known example we have. And so similarly, if we want to do a similar search for technosignatures, we can take the example of Earth and look for Earth-like technosignatures. So why atmospheric technosignatures? Well, the upcoming space facilities, telescope facilities, are focused on the characterizations of atmospheres using spectroscopy and observation of exoplanets. And so the search for biosignatures on these exoplanets utilizes this technology and this methodology to detect signals of biology or habitability or inhabitants. And so the idea here is that can we use the same telescopes, the same techniques, and the same instruments to observe any potential technosignatures? We don't have to do anything special with that. We just need to, if the data is there, can we look for the signals that we want to look for that can give a sign of technology? Is it even possible to do that? There were studies that were done on biosignatures, gases, to take the biosignature gases with these telescopes. So we just wanted to see if we can do the technosignatures as well. And one of that technosignature gases that we want to look for are the nitrogen dioxide. And we had this paper last year. And why nitrogen dioxide? Well, the nitrogen oxides are among the main pollutants of an industrialized civilization, at least for Earth here. They are fossil fuel generated. Okay, so if it is a fossil fuel, it must emit nitrogen dioxide. There are non-anthropogenic, non-human ways of producing nitrogen dioxide and human-generated ways as well. Biology produces it, lightning produces nitrogen dioxide, wildfires, and those are the biology and non-biology together. Well, if we consider ourselves biology, yes, that should also be included in the nitrogen dioxide pollution. But if we focus only on human-generated ones, the vehicle emissions, industrial activity, factories, wherever we burn fossil fuels, that's where the nitrogen dioxide as well, it produces as well. So these are fossil fuel power plants. So if we can do that, then that would be a good thing to do, to detect. Currently, the anthropogenic emissions dominate the production of nitrogen dioxide in our atmosphere by a factor of 3 compared to non-anthropogenic ones. And so in this study, we just took only the human-generated nitrogen dioxides because we want to build a threshold at the minimum if you want to detect a nitrogen dioxide signal of only human generate or an advanced industrialized technology can generate. What would the signal look like? Is it even possible to detect that kind of a signal? On top of that, you can add any biological or non-biological sources, and that would give even larger signal, but you wouldn't know if it's coming from biology or not. And so we just took the anthropogenic one and tried to do it. Now, why did we do this? Well, the industrial pollution was observed to change during the COVID pandemic, when the global concentration of NO2 were observed to decrease by a factor of about 20 to 30, 40% over urban areas. I wish I could show you an animation of this plot, but believe me, wherever you see these hotspots in the industrialized locations in the United States, that was in January 2020, and because I converted this into a PDF, I cannot show you the animation, but by March 2020, those hotspots just disappeared because there were lockdowns at the time. And these are the NO2 emissions map. And so the amount of NO2 decreased over the last couple of months. So this is where we got the idea from, saying, hey, what happens? Can we even detect these minimal amount of NO2 that we are generating? Not localized to United States, but global NO2 emissions from our civilization. These are the questions that came up. Is it even detectable by any technique? Would biosignature gases dominate the spectra? Are they long-lived? We just talked about. And how much telescope time we need? Most critical one, right? We don't have unlimited telescope time. And so where does NO2 absorb? The x-axis here is the wavelength in microns, and the y-axis is the strength of the absorption of NO2 molecule. And the rainbow region is roughly the optical wavelength region that we are sensitive to. NO2 has a very strong absorption. If you look at the right plot, I've plotted both nitrogen dioxide and other gases as well, carbon dioxide, water, ozone, and oxygen. There's also methane. I didn't do it because it will be even more cluttered. The point of this plot is to show that if you look at the mid-infrared part of the spectrum, there are a lot of gases that overlap with nitrogen dioxide, so it becomes a little bit confusing. But if you look in the optical and UV part of the spectrum, which is where the blue curve is nitrogen dioxide, there is very, very little overlap with any other gas except for ozone. And even in that case, there is a sweet spot between 0.3 to 0.5 micron where the blue has a peak. And that's where we want to look at. Guess what? That's where the future planned telescopes, flagship like LUAR or HABEX, are going to look in that wavelength bands. And so we thought this would be a nice thing to look at and see if the molecule absorbs in the right wavelength region for the telescope. Can we even detect this? Is the detection strong enough to do that? Okay, so this is what I just said. The direct imaging technique in the visible band would be the most optimal one to detect this kind of NO2 emission. All right, so we took at that time, the LUAR-A architecture, which is about a 15-meter class telescope, and then try to see if we want to detect the current Earth level NO2, the only human-generated one, not including the biology and everything else. What would it look like, and what kind of a signal-to-noise ratio we can get? So the x-axis is the amount of observation time you would need with the LUAR 15-meter class telescope, and the y-axis is the signal-to-noise ratio. So it's a signal-to-noise ratio of 3, and I put a horizontal line at SNR of 5. Okay. So for Earth-like planets around Sun-like stars at 10 parsecs, roughly around 30 light years away from us, we would need about 600 hours of LUAR 15-meter class telescope to reach signal-to-noise ratio of 5. If you want to see a signal-to-noise ratio of 3, you would need about 300 hours of observation time. I'll come to you. I know you may have some questions about, wow, this is hundreds of hours. I have a backup slide. If we have time in the discussion section, I can come back to that and compare that with how much time we spent with Hubble Space Telescope or Spitzer Space Telescope to observe the deep field views, the ultra deep field views. And then we can compare that with the amount of time that we use for this kind of signature. Okay, that's good. That was the plot I showed you before was the present Earth level NO2 industrialized pollution. But the amount of NO2 has decreased over the last 40 years globally. So if you want to detect Earth 40 years ago, what kind of observation time you would need, right? So, and that's not too different. You would probably need less than 600 hours, probably around 500 or 400 hours to reach a signal-to-noise ratio of 5 with the LUAR 15-meter class telescope. And that's actually twice the amount. Earth had 3 times over the NO2 40 years ago. So the time needed to observe this signal would be even less, probably around 300 hours or so, if you want to detect Earth at 40 years ago with this kind of pollution. So what I wanted to point out is the industrial pollutant like NOD is possibly detectable with upcoming telescope facility. It is not impossible. The signal was not so small that we would need like thousands of hours of observation time. It was within the reach of hundreds of hours. And just like biosignatures, there is no single gas signature is a sign of technology or biology. You would need the context, you would need the combination of gases, you would need the star-planet interaction or the information about the planet. So just like biosignatures, we would need multiple molecular features to observe technosignatures. So for example, NO2, CFC, radio, for example, we would need all of them together. Radio is an unambiguous one, in fact, I would say, if we can remove the false positive that we were thinking about. So I'm going to end this here. The question, are we alone, which has been a driving force to search for life, is a question posed by a technological civilization, which is us. So it's a matter of what kind of technology that we want to detect it, and how long such kind of technology can live on. There are some caveats about this plot and also some good things about this plot. So I could discuss this if we have time, but I want to advertise a Technosignature poster by Daniel Angerhausen, a machine learning assisted search for technosignatures on the moon using the LRO data. Any kind of anomaly is what you can find. And you can see it's on Wednesday, 11 to 11:15. Or talk, sorry, it's not a poster, it's talk, 11 to 11:15. I think I'll end there.
So we'll have a discussion time at the end of the session. So if you have any questions for Ravi, just keep them in mind, and then we'll have questions for all the speakers and discussion at the end.
Oh, yeah, just go. So should I stay or?
I think we'll move on.
We'll move on, okay.
Yes. So we are heading to the next presentation by Adam Frank, who will speak about triggering a climate change-dominated Anthropocene. Is it common among exo-civilizations?
All right. Can everyone hear me?
Yes, we can.
Good. Okay, and you can see my screen, so let me begin. Let me start my little timer so I don't go over. Okay, so the question for today that we're asking is one that can go under the idea of the astrobiology of the Anthropocene, which is of interest both for us as a civilization facing an Anthropocene, but we can also ask whether or not these kinds of transitions are generic. And I want to show you some research that we have done. This is work that actually was really spearheaded by an undergraduate, Ethan Savage, who's now going to the University of Florida, did amazing work. And then also Jonathan Carroll Nellenbach, my longtime collaborator, and Jacob was part of this as well. So we had a lot of fun with this together. And then also Axel Pleiden and Marina Alberti. Okay, so what we're talking about here is, falls under the idea of coevolution, that life and the planet evolve together. So this is something that is discussed quite a bit in Earth systems science. And you can look back to the history of the Earth and see many examples where life is affecting the evolution of the planet, and then the evolution of the planet is affecting life. So we really don't want to think of these as two separate systems, but that actually one co-evolving system. And the idea should be that once you get a technological civilization, that is just another example of this, billion-year evolution and interchange between life and the planet. Now it's just, what we might call technological life. Now, there's a great deal of discussion about whether or not there are going to be generic classes of trajectory for the evolution of biospheres, the evolution of life, right? So will there be should we expect biospheres to develop forms of life even, molecular, metabolisms that will be in some sense similar to anything that's happened on Earth. And this is an ongoing debate, of course. People, so there's this question about wings. So I give these two examples of wings, right? Nature on Earth has stumbled upon wings through a lot of phylogenetic pathways or genetic pathways. Now, people like David Catling would argue that, one example of this would be just oxygen. That his claim is that oxygen, molecular oxygen, is really the most powerful and potent kind of chemical you're going to use for building life, and that should happen anywhere. And this doesn't necessarily have to be about chemicals or structures, it can also be about information. Kim et al., the Arizona group, which is extraordinary, has done work looking at sort of how the informational topologies, the network topologies for life and Earth at different scales are very similar, and perhaps that's an indicator that you can think of that as a convergent evolutionary trajectory. And then, of course, in technosignatures, the most obvious example of this is the Kardashev scale, claiming that there was these types, type 1, type 2, type 3, and these would be a natural progression for any civilization in terms of energy harvesting. All right, now on Earth, our energy harvesting, among other things, has led us into what has been called the Anthropocene, which is, we are currently in the geological epoch known as the Holocene, which is the current last 10,000 years interglacial period. But it really looks like human beings, through their activity, are going to arrest that, are ending the Holocene, and that we're entering something called the Anthropocene, which is marked by human activity, where human activity is the principal driver for the Earth's systems, for their functions and their, what is pushing them around. And there's, lots and lots and lots of evidence for this. I don't need to go into this. So I will take it as a given that we have entered the Anthropocene. And then the question is, this topic that Jacob and I and others have looked at is this idea of the astrobiology of the Anthropocene. If we think of the Anthropocene as being a planetary transition, then we can ask whether or not this is something that any civilization might drive. And so the questions that come up that you want to ask about the astrobiology of the Anthropocene, and eventually the technosignatures that might be associated with it, are how common are they? And of course, we're putting this in quote, right? Because if it's a difference, it would have to be a Borgocene or a Klingonocene or whatever. How fatal are these? Do Anthropocenes always truncate evolution, or do they the evolution of a civilization, or do they just delay it for long periods of time? And then from the technosignature side, what properties might we expect these civilizations that have undergone Anthropocenes and gotten through them? What properties might they have? Now, we have done work on this before, so what I'm going to show you is new work on it, but I want to remind you of the old work. This paper, Frank et al. 2018, where we did a modeling where we had a model for the population of the civilization, that's N here, and then the model for the environment as well, which is E here, and you can think of it as temperature. And we did coupled modeling between the population and the planet, with the planet responding to the population's feedback. And what we found is that there were three classes of trajectory that in the models. There was green here is the population, and red is the planetary, we can think of it as temperature. There's what's called the smooth landing, where the planet responds to the population, but everybody comes into a new equilibrium. There was also the die-off, which I'm pointing to here, where the population overshoots the planet's carrying capacity and then drops, quite strongly, and you may lose, a considerable amount of your civilization, and you can ask whether or not a technological civilization could still function under those conditions. And then finally, we also had complete collapse, which is really what you're hoping to avoid. But now these models were pretty simple in the sense that, especially the environment, the model for the environment was a toy model. So what we want to do now is go forward, and this is the new paper. And the main thing we're going to add here is we're going to think about civilizations that use combustion in one form or another, and ask about how they are going to change their planets using a 1D climate model. So the model we used, Jacob provided it. These are the authors who sort of, developed and used it. And it's basically, it's a latitudinal model But we're going to average over the model. We're going to get just a one planetary temperature, but at least it allows us to actually, do a climate model, get a temperature out of that, have that temperature feed back into our population model. So down here is just this is just temperature versus distance on CO2. What we're really showing is we recover the habitable zone. Basically, this model does a nice job of recovering what everybody knows as the habitable zone. So, okay, that's our starting point. To this, we're going to add a population model. N is the population of the civilization. We don't need to look at this in detail, just that there is going to be, we're going to have an enhanced growth rate due to technology, where P, which is the partial pressure of CO2, is going to be indicative of that enhanced growth rate. And then there's also going to be a diminished growth rate due to temperature. So basically, if you're creating CO2, that's indicative of the fact that you're harvesting energy. Harvesting energy is good for increasing your population, but as that feedbacks on the planet and the temperature rises, you're going to start once you get past the delta T, the range of temperature that the population can handle, you're going to start having increased death rates. And we note that the CO2, P is the partial pressure, is going to depend on the population. So the population is going to generate CO2, and CO2 is going to feed back. All right, I won't go into this in any detail. I'll just note these are just the important parameters of the model. And what we're going to call a climate-dominated Anthropocene is one where you see strong population decline before you've hit the carrying capacity. Okay. And what we're also going to be interested in is what's called the complex life habitable zone. And we can talk about this in the discussions, which is basically, CO2 for life on Earth is pretty dangerous once you get past about 5,000 parts per million. And so we're not going to be interested in planets that go beyond this. So we're only going to do our models. We're going to apply our models to that ring of orbits where you can increase CO2 to make your planet habitable. But if you have to increase your CO2 by dumping huge amounts into it to get the planet get the temperature to be warm enough for life, for liquid water to form, then we're not going to include those in our models. I will note that we used the models. We first tuned the models to the population growth on temperature rise on Earth for the last 100 or so years, and we got a very nice response, so that was good. And then now let me show you the models, where the most important parameter in the models is this factor gamma, which is the growth time of the civilization divided by the response time of the climate. And so if gamma is low, that means the civilization can grow very quickly and the climate's not going to know about it. And here is one of those models, population on one side and temperature and CO2 on the other. And what you see is the population grows up to its carrying capacity, makes it all the way up to the carrying capacity of 20 billion, okay? And then slowly starts to decline. We can talk about why this is, but basically this civilization is not going through an Anthropocene. This civilization with gamma of 181 is very sensitive, and it is going, as you can see, it's going to go through a climate-driven Anthropocene. The population rises and never gets to 20 billion. You can see it gets to much less than 20 billion and then drops to the point where you've lost a fairly large fraction of your population. So we do see Anthropocenes in our models, and this is sort of the important takeaway. Here is distance versus temperature for two parameters for the model. This is the time to decline by 20% of peak population, and you can see that in this entire band here. After a few hundred years, you lose 20% of your population. And so also we can also calculate the collapse time, which is another indicative feature of how quickly you're dropping, your population is dropping. And what you can see here is that the collapse time is less than a few hundred years in this entire band. So pretty much anywhere that's in the complex life habitable zone, you almost always trigger an Anthropocene. So it's actually pretty hard to avoid triggering an Anthropocene. Now, just to conclude, I'll note that this delta T is an important function because we know that delta T is what, we don't know really, we don't know the climate sensitivity for our own planet, right? We know that probably human beings, once the temperature gets too high, human beings will die. But as the climate changes, we don't know whether or not the civilization can really hold together. So here's what you see is the log time to decline by 20% as a function of delta T. And you can see when delta T is small, just 0.5, 10K, that after 100 years, you lose a huge amount of population. And for 10K, if you're less sensitive, then you can get out almost to 1,000 years without having a lot of civilization being lost. So, so our conclusion is that, yeah, for civilizations or for creatures like ours, it's going to be hard to avoid an Anthropocene. It's going to be hard to avoid triggering some kind of climate feedback if the energy that you're using is combustion based, which we would argue is probably where you're going to start. Most civilizations, we would argue, burning biomass is going to be something that's going to be very easy to find if you're a young civilization. And so we would argue that that is a likely candidate to start your civilization with. And that means it may be hard it may be difficult to avoid a Anthropocene. But finally, I just want to end on this note, looking at these two different books, Sapiens and The Dawn of Everything, because these are two very, very different books in their telling of the story of human civilization trajectory. Sapiens kind of has this usual big history argument that there's an inevitable path from hunter-gatherers, egalitarian hunter-gatherers to industrial, complex, top-down civilizations. And this new book by Graeber and Wengrow argues that actually there's been a plethora of kinds of forms of human political and technological forms. So this book I don't know what to make of it, but I think it's something, and when we try and think about the evolution of civilizations, we may want to think about ergodic possibilities, that you explore a lot of parameter space. So I'll end there. Just my conclusions are complex life, habitable zone. They'll probably be common. Temperature sensitivity matters a lot. And in terms of technosignatures, it may be that we're looking for evidence of planetary system changes over time. That may be a technosignature. And then this also, for me, raises general questions about the problem. So I will end there. I've stayed within time and stop sharing.
Thank you very much.
Thank you.
So again, save your questions for the discussion session at the end.
Yes, write down your questions. Good idea. Well, so the order here on the screen is not the correct one. It's first Timaraju, who will speak now about a way to classify technosignatures that is called Technosignatures Gap Study List, and how we can observe them.
Hi, everyone. Let me start sharing my screen. I'm Virisha Timaraj, and I'm a data scientist at the Jet Propulsion Laboratory. And my collaborators for this project are Nick Siegler, who is the chief scientist of the chief technologist for the Exoplanet Exploration Program, and Eric Mamajek, the deputy chief scientist for EXEP. So today I'll be presenting on the Technosignatures Gap List study, which has been funded by the NASA Exoplanet Exploration Program. So EXEP has been chartered to search for habitable worlds and identify the required technologies to enable that. So since Technosignatures is a part of that goal, EXEP was interested in creating this fact-finding study to look for to inform themselves of the overall technosignatures landscape. And I've been tasked to lead the study to ultimately create a publicly accessible unified database that would essentially also serve as a repository of information for the technosignatures community. So in order to do that, initially at the start of the task, a panel of experts was assembled to continuously review and provide feedback on the process. And to jump into the approach itself, we started by putting together a set of potential extraterrestrial activities and the technosignature search approaches associated with it. So across that, identifying what are some of the data fields that can help the users use this database to answer some questions related to their interests. in the field. So two primary types of data fields, descriptors and assessors. Descriptors would be all the informational fields like that would describe the possible extraterrestrial activity itself or the approach. And the assessors would help them sort through the database to get like a filtered view of everything. So going beyond that and completing or like compiling the entire list of Peters and the search approaches would be the next step. And of course, like filling out the entire data fields for all of these Peters and search approaches so that the database can be made complete. So in doing this, like we wanted to kind of start with the descriptors and assessors, but what are some of the most interesting findings that came out of the study was the possible extraterrestrial activities. So it was interesting to find that most of them can be broadly categorized into one of these four categories, going from just alien generated like technological remnants to just byproducts of everyday activities by the aliens, or artificial megastructures that are built by them, to communicating communicating to their counterparts across the universe. So it was interesting to see that most of the reviewed Peters fall into one of these categories. But now, how do we take these and map them into like all of the search approaches that exist to detect these activities? Sophia suggested this way to kind of look at the technosignature search approaches was that in each search approach would be mapped to some activity. So let's say there is the Dyson sphere technology, which would have several TSAs that can detect it, but they're all derived from a certain motivation. So depending on the motivation, we can take the TSAs down to the technology level and make them very specific. So we incorporated this framework and created the technology motivation TSA framework for the database, which starts with, just as an example, the interstellar artifacts, let's say, which would be the possible extraterrestrial activity. So the first step would be to identify which category the activity falls into, and then moving into what is the motivation behind the PETA, either exploring the universe or observing activities on the Earth, as an example for this, and then identifying the search approaches associated with that, whether it's like detecting flybys using direct imaging or spectrophotometry. So seeing that difference in different technologies associated with the search approaches, or detecting lurkers versus looking for surface technological remnants. This is still a work in progress, but and what is presented on the slide is just a subset of all the various motivations and PETAs and TSAs that exist in the database. So for the TSAs that have been identified, what is the information that we can provide in the database that the users can can utilize? So two types of data fields, like I mentioned earlier, the descriptors and the assessors. The descriptors would be any activity that the ET is doing and what the humans are doing to detect it. So just as an example for the previous interstellar artifact case, it could be what is the motivation behind the PETA, what is the intention in being found, and the longevity of the signal that Jacob talked about a little bit earlier in the discussion. Like how long-lived is the signal itself, and is it continuous or discrete? And for the humans detecting ET, that would be the search approach. What is the observable? What are some of the technical challenges that are plaguing the field right now? And what is the search location? Or what are the upper limits of the TSA? Would be some example descriptors that we have incorporated. And the assessors would be anything that the user can sort the database on and get answers to things that they are most interested in finding out, and just getting like a filtered view. So some examples would be the ancillary science benefits for someone in a different field, scientists in different fields, kind of looking for what other techniques, what other like benefits could within the technosignature field that they can address. and what is the technology state of the art, like, and to kind of then derive the gaps in technology and look for where the most needs are, and any other needs beyond the technology, like funding or workforce or even like facility needs, etc. So all of these fields have been like, so here, this is just a subset of all the data fields that have been identified. In total, there are 14 descriptors and about 18 SSRs in the database. So the final database would look something like this, where every column would be a unique technosignature search approach, and that would be mapped to a broad category of PETA. And every approach would then be tied to several descriptors and SSRs to provide information. So how can one benefit from this? So there are broad categories of users that this can really help, from new researchers in the field to philanthropists to NASA program managers to general public. Based on the questions that they're trying to answer, they can sort the database using the SSRs and descriptors and derive like a filtered view, like I mentioned earlier. For example, if there was like a future mission designer for the decadal survey, for the decadal flagship mission, they could look through this database and identify which technosignature search approach could be like concomitant to the mission that they're building. So this could be really valuable to many types of users. And so looking forward, we would like to finish compiling this list of TS approaches across all the extraterrestrial activities that have been identified, while we still are challenging ourselves to find PETAs that don't fit into the 4 categories that we've identified, and also to go ahead and like complete the full database and fill in all the information about each of the approaches and PETAs. So this, I would like to conclude by saying that since this is a database that is being made for the community, we would love to hear from the community, and I will reach out to some of you in the coming months as well. But if you have any input or resources or comments or feedback on any of this, please feel free to reach out to us, and we would love to hear from you. Thank you.
So our next speaker is George Profitiliotis, and he will speak about and demonstrate something in line with a previous talk, a Delphi approach to technosignature prioritization. Thank you.
Yes, thank you. Can you hear me? It's fine. Let me try to share the screen. All right. All right. So can you hear me?
Yeah.
Great. I'm going to present today an idea that originally was developed during was first discussed during the Technoclimate conference, and that's why it was initiated together with colleagues Sophia Seich and Clement Vidal, who is also there. So I'm going to speak on behalf of my collaborators as well. And I will try to present a tool that could be used both in real time and asynchronously to give experts in the technosignatures community an opportunity to participate in prioritizing technosignature search strategies. So as you might already know, there is a large number of potential technosignature targets and strategies that are being proposed in the literature. And you may have already seen the Breakthrough List and Exotica catalog that more than 800 distinct targets. And in in an effort to facilitate the prioritization of the potential searches of proposed technosignatures, since the resources are very limited, Sophia say initially put forward a conceptual framework with 9 fingers of merit that was called the 9 axes of merit, noting that the axes should not be used to entirely exclude areas of research, but to prioritize some technosignature research strategies at this point in time when the field is heavily constrained by funding and other kind of obstacles. So you may have already seen the axes, but you can refer to them here on the left. The first figure of merit is observing capability. So search strategies that can be done right now are considered of higher merit. The second one is cost, including all kinds of capital that is needed to conduct a search. So any technosignature searches that can be done cheaply are considered of higher merit. The third one is the ancillary benefits. So if a search has many ancillary benefits, then it is considered of higher merit. Similarly, a search that is looking for a technosignature that is detectable is also considered of higher merit. And also a search that is looking for a long-lived technosignature, again, is considered of higher merit, as well as searches that are looking for technosignatures that have a high signal-to-noise ratio with respect to the background, so they are unambiguous, and they do not require a lot of, let's say, imaginative extrapolation from the current technology that humans are capable of doing right now. And also another figure of merit is the inevitability of a technosignature. So this means that if we don't need many assumptions regarding the psychology or the sociology of the entities behind generating this technosignature, then we can consider this search to be of higher merit, as well as searches that can provide a lot of information. We have a chance to review the axis again in a few minutes. So for today, I'm going to present the case for using the Delphi method, a method from Foresight, as a way to prioritize technosignature searches using the 9 axes of merit. And we will also demonstrate practically in real time how this could be done. So the Delphi method was originally developed by RAND, a think tank in the early 1960s, as a tool for foresight and forecasting issues. This method is used in judgmental forecasting and in judgmental foresight, where there is deep uncertainty. And it was specifically designed to remove any conference room impediments, to give an opportunity for a group to reach consensus without all the negative features of group discussion, limited time, or any sort of domineering opinions that may undermine the effectiveness of the discussion. So the Delphi method is based on the following principles. The first one is anonymity. The second one is iteration. The third one is controlled feedback of responses to all the group members. And the fourth one is the statistical aggregation of the individual responses. To do that, the designer of the Delphi method usually tries to locate a group of experts that are asked to respond anonymously to a sequence of questions for a specific theme. Then the opinions are aggregated and they are fed back to the respondents with in the form of a statistical summary. And also respondents are given the opportunity to discuss their reasons for stating what they have stated when answering the items. And when the participants are presented with the aggregate responses of the group, they are also given the opportunity to submit a revised response after considering what has been submitted by the group, or resubmit their first response. And this is the iteration part of the Delphi process that can give the opportunity to the group to reach consensus. Of course, consensus is not a mandatory condition, but there are some best practices out there that can lead to a good design of a Delphi method that could potentially lead to consensus. So today we're going to try the real-time variant of the Delphi method, which is, as what I said before, with the only change that the rounds are occurring one after the other in rapid iteration. And we will use a transformation of the 9 axes of merit based on the concept of semantic differentials that has already been used in the literature of the Delphi studies. And in this conceptualization of the axis of merit, a standard scaling technique is used to create a reference, create a scale with 7 reference points between 2 bipolar contrasting adjectives or a cluster of adjectives in our case, with a neutral midpoint. So you will see 9 items with such scales in an online form that we have prepared. And let's start immediately with illustration. If you have your smartphone or a laptop, you can scan the QR code with your smartphone to get to the form. And if not, you can type in the URL here. And I it for a little while so that you can access the survey, and then I can show you how the demonstration can occur, although there are detailed instructions in there, and I think that we have a lot of time to complete it. So if you scan the QR code or type in the URL, the shortened one or the long one, you will be presented with a main screen. Perhaps I can shift what I'm sharing to show you what it will look like. It will look like this. You have to click on the Start Survey button. Then you will be presented with the instructions where we are asking you to contemplate on a specific technosignature search strategy, which is the search for waste heat from megastructures. So this exercise focuses exclusively on searching for the waste heat emitted by megastructures that can be observed in infrared wavelengths. And you will see here the transformation of the 9 axis figures of merit in the form of the semantic differential scale. If you are not sure what the axis means, you can click on the small question mark here. You will find a small description, short description on below. And the first time you click on saving your response, you will be presented with a window where you can submit your email to get a link to review the results of the group afterwards. So if you didn't manage to do that, then there is, if you missed that window, then when you reach the final axis, just click on the Return to Start page button right below the Save button. Don't click Submit. I mean, if you didn't manage to give your email to the platform, don't click Submit. Click on Return to the main page, the Start page. When you return the Start page after providing your judgments, you will be presented with the aggregated responses of the group, and if you want, you will be given the opportunity to revisit your judgment. And there is a button that says Edit Answer. You can click that, and then you can submit a second judgment, perhaps taking into consideration what the group has voted on. So let's see if we have some results here. We have some results. All right. I'm not sure how much time we have. Perhaps we can see some of the results here. All right. So in order to see if consensus has been reached, you have to do some post-processing, but we can already see that there is, yeah, Let's see if I can refresh that. The meeting has changed. Yeah, so as far as we leave the survey open, you can come again by clicking the link and iterate on your responses and provide a revised judgment if you want. So that would give someone the opportunity to gain feedback on the group's aggregate results, and afterwards one can process the outputs, and if the quartile deviation of the values of the items collected by the experts is lower than 60%, then according to the literature, that is considered consensus for an item. But we will have to do that afterwards. So yeah, the next steps, if I have a minute, the next steps would be to collect the, first, you have to deploy this massively, collect the judgments of the experts from expert community, and then these axes are not weighted. So we have to weight the axes themselves. So we have to run a similar process to find the relative importance of each of the 9 figures of merit, the 9 axes of merit themselves, in order to find the weights, how much each axis should contribute to the overall value, let's say, of merit of a specific technosegment research. And if we manage to do that, then combining the Delphi method with another appropriate multiple criteria decision-making method might enable the community to collectively conduct exercises of relative prioritization among potential searches for technosignatures without excluding candidates. But if you run this very frequently, then candidates might be able to move up the ranks, and we propose that this should occur in a regular interval, so that the list should not remain fixed. That's all. I would be happy to answer any questions. I hope you managed to revisit any of your responses, and I hope it worked.
Yes, it works very well. Congratulations for setting this up. I have a question about this real-time Delphi. Is it possible to write text in free form to comment on the different replies?
Yeah, right now in the platform as it is, we cannot, we have not given the opportunity to participants to comment, but yes, you can have participants provide rationales as to why they voted on, like why they have selected a specific point on the scale, and then there is also the option for others to comment on these rationales. So even if there is not consensus, if in the post-processing it seems that some items have, like there is dissent on some items, perhaps the discussion in the comments could provide insights on why there is a disagreement. But I have not included that in this demo presentation, just to make sure that it works in real time. It's the first time it happens in a conference.
Yes.
Thanks.
Okay, I guess we can thank George.
Yeah, thank you very much.
Thank you so much.
So now we have time for discussion. We have a little bit more than 20 minutes. So you can ask questions about any of the talks you saw this morning. And I don't know who has a microphone for the audience.
We do have some questions online as well.
Okay.
Hi there, thanks for all the talks. Actually, my first question is to you, Ravi, and probably also to Adam a little bit. For the stuff that you showed related to like nitrogen dioxide being a possible technosignature, I guess I see kind of like a paradox between this idea that as humans on Earth, if we want to kind of persist over long periods, we need to stop using pollutants, but then also using pollutants as a possible technosignature. I wouldn't expect them to be kind of long lasting on planets because it seemed like if you need to survive for a long time, you need to get rid of them. So how do you kind of like think about the kind of probabilities of these timescales?
Well, the work that I presented is that if you have something on the planet that resembles the kind of pollution or the technology that we, industrialized technology that we have, would we be able to detect it? Doesn't necessarily mean that they would exist there, and they may not be long-lived, actually. Like you said, for a civilization that need to survive for a long time, polluting your atmosphere and then trying to sustain it may not be possible. As far as, what's the question for Adam?
I mentioned Adam because it seemed like also your work, you thought about kind of timescales of, human caused, signatures and that kind of thing. So I think maybe you thought about this too a little bit.
Yeah, we have. I think, after thinking about this for a while, I don't think it's true that long-lived civilizations disappear into their planet. I mean, certainly, in order to be a sustainable technosphere, you need to integrate yourself into the biosphere, right? So we just recently did a paper, David Grinspoon and Sarah Walker and I, on planetary intelligence. The idea that, what does it take for a biosphere to become long-term? What would it take for a technosphere to become long-term? But it doesn't mean that you disappear, because integrating into the biosphere for a energy using a civilization that's using a lot of energy would probably mean that you're still visible in some ways. Like you're making the biosphere vibrant, you're increasing biodiversity, you're certainly reducing dangerous chemicals, but that doesn't necessarily mean that you're not producing any technosignatures. In fact, if we're thinking about dissipation as a mechanism or as a technosignature, then dissipation I would expect it actually to grow. And that may be apparent in the chemical networks, in the energy networks. So, long-lived, high-tech civilizations, I think, don't sort of, disappear into their biospheres. That's the way I'm thinking about it now.
Oh, sure, go ahead.
I can read the online question whenever you.
Yeah, go ahead, read the online question. We were wondering.
Sure. So this is from Dr. Mark Elowitz. Wouldn't SF6 be a smoking gun technosignature since it is only produced synthetically by industrial processes? Does SF6 even have a natural background source?
Well, I can comment on that. That's a great question. And Eddie Schwederman, who's here, is leading an effort to study that, SF6 and other artificial greenhouse gases. Is Eddie here? I don't know if Eddie's in the room here.
Do you want to? Do you want to comment? Jacob?
Yeah, so we're working on it. It's certainly SF6B. If there was, I think 1 part per million is extremely detectable in the infrared. So it's not great for humans, but yeah, if you were terraforming a planet or something like that with SF6, CFCs, any kind of these industrial gases, yeah, the question, would you want pollution on your planet? Maybe it wouldn't be good for us, but maybe we would want to do that on Mars to make Mars warm. So you could really think about that. And certainly that would be a pretty unambiguous technosignature molecule compared to others.
Hi. So several of the talks today talked about the emissions of fossil fuels. However, given that fossil fuels are present on Earth only because recalcitrant carbon compounds like lignin evolved millions of years ahead of time before fungus that had enzymes capable of breaking them down, can we assume that's always going to be the case?
I think biomass, maybe not burning fossil fuels, but combustion is something that's going to be common because, when you think about what energy sources are available to a young civilization and, burning, biomass by its very nature is probably going to have a lot of energy content in it. And you've got lightning around. And so I think combustion may be the first thing that you stumble on. I mean, I'm happy to talk about other ways it can happen, but when you think about what's readily available to a young civilization, burning something becomes seems obvious.
I also want to add something that even if civilization develop into being cleaner, just because of the second law of thermodynamics, we need to dissipate waste and entropy. So it's something universal, like pollution has to happen for any active living thing. But the question is, yes, what kind of pollution and how can we detect it?
Right. So I want to point out that it's not a single signature is not a technological signature. You need multiple ones. So if you find NO2 on a planet, you may not know that it's coming from biology or wildfires or something happened or from technology. Something else needs to be happening on the planet to have a confirmation on it. For example, I wanted to ask actually to Steve or someone that is radio technology also short-lived? Because if an industrialized civilization can have this kind of a phase, radio wasn't there before, so how long we can expect it to last?
Yeah, I guess we don't know. We've had radio technology for 100 years here on Earth. Is it going to be superseded by something else? There's certainly been a lot of change in the way that we communicate as humans over the sort of lifetime of humans as a species, but radio is also sort of a very efficient way of communicating. The electromagnetic spectrum generally is an efficient way of communicating at interstellar distances. So, we can sort of hypothesize within the limits of the physics that we know now about other ways that you might communicate over long distance, gravitational waves or something, or neutrinos, or it's kind of hard to say sort of how long it'll be till something better comes along. But what we've got is pretty good and pretty efficient, I think.
Interesting, there's all these questions about the lifetimes of the signals, and Ravi's talk on this, where he alluded to that right before Adam's, had me wondering for Adam, or anyone, if you were thinking about or talking about modeling the pathways that a civilization might take and its changes in, say, greenhouse gas emissions and temperature over time. If you look backwards at our own civilization here on Earth, I'm thinking about both the NO2, but also like the CFCs. If you plotted the trajectory of those gases, do they fit any of your models? And I'm thinking also, like, if they did, would that be both predictive of our future, or could we look for patterns where, a civilization sees a temper? You have to have a long baseline of observations to catch this, but could that also be a leading indicator of a civilization that goes to one of your end state trajectories, perhaps a better one?
Let me just answer that quickly, and then others can chime in. I think it's a really interesting idea, and it goes exactly to Ravi's point that a single molecule is not a technosignature.
There is feedback.
Okay, thanks.
Who is the question going to?
There is another question coming up.
Okay.
Hi everyone, Thomas Mouchet from NASA Goddard. So thank you very much for this very, very interesting session. I have a question for everyone, or maybe more specifically for Ravi. So let's say that we detect some NO2, CFC, any kind of pollutant, SF6, on an exoplanet atmosphere, but that exoplanet is very outside the habitable zone, either way too hot or way too cold. How will you interpret that?
By jumping with joy. If we find any of these multiple signals on an exoplanet that is not in the habitable zone, that does not look habitable, and we find CFCs and NO2 and some other, potentially technological gas or signal, what do we do? How will we interpret that? carefully. Because we should first remove any potential geological or biological sources that we could, come up with. And once we eliminate those, any other sources, and we cannot think of anything, we would carefully say that, we cannot explain it. We will not say that's arising from technology, that we cannot explain. We will say we cannot explain it based on what we know about the physics of, the planet or, geological activities. And that's as far as I would go in announcing any potential discovery. Because there could be processes that we will never be able to think of that could result in these false positives, just like Sean's work on false positives in biology.
One thing I can add to that too is we didn't talk about in the session the idea of graveyard civilizations. So NO2 might not fit this, but if you saw CFCs and anything that has a long lifetime, I mean, maybe there was a planet that was terraformed and then it died out, and you're observing sort of the longer lasting atmospheric constituents, in a too hot or too cold planet. So that could be one scenario. We couldn't obviously conclude that just from the observations, but that would be one possibility that we could, explore.
I think in this context, one other advantage of the terraformed planets versus the ones where it's just waste is that we probably, from the observing strategy point of view, will have a better strategy to observe them. Right? We probably look at planets and then we figure out there's something at the edge of the habitable zone that is much warmer or much colder than it's supposed to be before we even get spectra of them, right? So like if we do, let's say, a mid-infrared spectrum of a planet and we see it's hotter than it's supposed to be, then we can say, okay, maybe we analyze that deeper to find that SF6. So this terraforming thing gives you a first step to kind of like go down which planets to analyze farther.
Maybe it's a failed attempt at terraforming too. Terraforming might be really hard.
Yes, I would like also to add to what you said, Ravi, about not one single gas would be any kind of proof. And I think also not multiple gases would be a convincing proof. So in a way, I like the approach of Adam to look at the dynamics, to look at how these gases evolve in time. And I mean, that's what science is about. It's about making predictions. So if you say, well, these gases are due to technological activity, and therefore, if we look at it next year, next 2 years, it should increase in this way, in this proportion. And then if this is validated, then I think a case could become much stronger.
Hi, so my question's for Varisha. I was wondering what the timeline is for that database being publicly accessible, and then also if you envision NASA maybe using something like the Delphi method that George shared for like community discussions on, I don't know, deciding which directions to focus on. Thanks.
Yeah, so I think to answer your first question, the timeline we're looking at is like in the coming maybe like 4 to 5 months is when we assume the entire database will be complete to the best of our knowledge and be published. And for the next question, yes, we were just talking about it in the chat right now, and George and I will tag up later and make it happen.
Great, thanks.
I also have a question for you, Girisha. So George presented the axis of merit to evaluate each technosignature. And in your approach, you have assessors that are specific with each technosignature search. So what do you think about the pros and cons of having assessors specific to a technosignature strategy and search versus having axis of merits that could potentially apply to any technosignature?
Yeah, so the SSs that have been created actually include the axis of merit as well. And like in addition to that, there are some fields that kind of have been created to like for the broad community of users, like keeping that in mind, like if there is a new researcher in the field, they would be interested in identifying where the opportunities are. So so that was the basis for how the SSS was created. So it's specific to the user as opposed to being specific to the technosignature approach. So they are pretty generalized.
Hi, my name is Erin Kanji. I'm a PhD candidate at Boulder, and this question is for George. Very interesting demonstration of the Delphi method, which I did not know about. Thank you for that. And I'm just wondering if when this technique is used across different disciplines and different topics, if folks who use it have noticed any sort of trends toward like reaching a sort of middle of the road or more conservative consensus. I could kind of imagine that folks who wanted to express like a high risk, high reward opinion might sort of stick out and eventually sort of, come back to the middle, if that makes sense.
Yes, absolutely. Thank you. Thank you for your interest. Yes, the Delphi method developed specifically for forecasting or for decision making. So it has been widely used in the health sciences where expert opinion is highly valued. So you may find very like a lot of examples in the literature using the Delphi method in various variants and versions of the Delphi method to help nurses or clinicians or any other health professionals reach some sort of standards, let's say, of practice by discussing in a structured format. So as you said, indeed, the Delphi method might, like if you want to reach consensus, it might bias, let's say, responses to converge towards a consensus, but it does not mandate it. So it is possible for high risk, let's say high reward opinions to emerge in such a survey. And that's why usually you need multiple rounds. We just demonstrated this in real time because there is a real time variant of the Delphi method. But you will need to do this over months. It's a lengthy procedure where you have also the option of you can give the experts the option to explain the rationales in free form, and then you have the people managing the survey aggregating and collating the results and presenting the information to the others. And if the others can be convinced, perhaps of the merits of a high risk, high reward approach, then the median might be shifted. So it's let's say it's a structured dialogue. It's not so much of a survey than of a structured dialogue that also gives the opportunity to the respondents to reach disagreement, that they agree, that they disagree. So if there are metrics that you can use to show that there is strong disagreement over some topic, and then you can dive deep and see why there is disagreement, why there might be assumptions built in the systems that cognitive systems that the respondent deploy when they are responding to the items. And there are other methods that you can use to try to reach to the root of that, or you can resolve it. There are other methods like the nominal group technique that you can deploy right immediately afterwards. So there are some let's say setbacks, but you can also find ways to mitigate these. And in the full-scale version of a multiple round, let's say Delphi process, even high risk, high reward opinions would be represented, and they would be given the opportunity to explain the rationales and perhaps convince, let's say, rhetorically convince the other experts that there is merit in their approach. So it's all judgmental. It's not qualitative per se, it's semi-qualitative, but it uses best available knowledge, let's say, that is the expert's head. So it's an expert judgment method that is the best that you can have when you don't have enough data to do statistical forecasting or try to feed statistical data to any other decision-making techniques. I hope I managed to respond.
Are there any online questions that we are?
Well, I can just make a comment that Varisha's talk made me think about is, I think it's interesting that you can fit all so technosignatures depends on motivation. I think is one of the things that came out of this in her analysis. At least, if you're going to search for something, many of these depend on the motivation of the hypothetical aliens that are doing this. Is this a distinction between, just a question to pose, it's a distinction between biosignatures and technosignatures? Are there biosignatures that depend on motivation, or are there not? And then that's really one of the distinctions. So I don't have an answer, just kind of throwing it out there at the end of the discussion. Maybe that's something to think about. And what is motivation? Is that tied to intelligence or cognition, or does it not matter? What kind of choices does biology make that could look like motivation? So something to think about. If anyone has any comments, feel free to share.
Yes, no, I think that's the crucial difference between the two searches indeed. And also that's a difficulty for technosignatures is to imagine what could be these motivations. But there are more or less conservative ways to approach this question. But yes, that's an additional difficulty, I would say.
I was thinking of the kind of, what is it, like a nature versus nurture. So you're talking about motivation, I'm assuming, I feel like it's based on kind of what you're given, whatever the civilization is going to start with, to a certain extent. Like whatever that planet setup is. If it's not like Earth, I mean, it could be something terrestrial, but, completely different kind of chemical bases or whatever. So that's when I think motivation, I kind of think that way. It's like, what are you given to start with?
So this is a shameless promotion. So if you want, there's a Technosignature seminar series that I organize at NASA Goddard. It happens, every month, 1 or 2 talks. And if you want to be added to that email list to receive these seminars, they are recorded and posted on the website. Just contact me after this session and I can add you to the list. Or if you want to give a talk at that seminar series, you're most welcome. Or if you know someone, a colleague who is working in that and want to recommend, even that would be great too. So,
thank you very much. I think we can close the session for today. Thank you to all the participants and the audience and everyone on Zoom.
And we have our next Technosignature session at 1 in Galleria 5.